So does it work? Okay. So good afternoon, everyone. Thank you for the introduction. The work that I'm going to present you today is a joint effort done with UPB from Bolivia, Università della Svizzera Italiana in Lugano, Switzerland, and also Oracle Labs. So as the title of the work already suggests, our goal is to propose a new methodology for automatically applying dynamic program analysis, that I will abbreviate as DPA, at a large scale on projects hosted in public open source repositories. And the main motivation for doing so is that applying DPA in large code repositories is increasingly important. For example, later I will talk about several use cases where applying DPA can be useful. Unfortunately, existing infrastructures focus mainly on static analysis, and that's unfortunate for us because many key properties of the workloads can only be studied with dynamic analysis. We implemented our methodology in a new distributed infrastructure for automated DPA at large scale, which we call NAB. So NAB automatically looks for executable code in public repositories like GitHub, GitLab, Bitbucket, etc. Here I will focus mainly on GitHub, which is the repository offering the most advanced search API. Then it filters out projects according to user-defined criteria, for example, based on the programming language, the date of last commit, number of contributors, number of stars, etc. And also it attempts to apply DPA on workloads that can be automatically executed. And we focus in particular on test code, because test code can be executed easily in an automatic way, assuming that the project is managed via a build system like Maven, NPM, SBT, etc. And all these activities are performed automatically by NAB without the need of manual intervention or user interaction. And this is a very important requirement when analyzing thousands of projects. NAB uses also containerization, in particular via Docker. There are several reasons why we designed NAB around using containerization technology. The first one is that it simplifies distributed deployment, which is fundamental to apply DPA at the scale of code repository and also obtain results in a reasonable time frame. Another reason is that it makes it easy to integrate different runtime, and so it is also easy to support multiple languages. In fact, NAB at the moment supports JavaScript, Java, and Scala. And another reason is that containerization provides a natural and efficient sandboxing, which is very important when analyzing projects in public repositories, since the projects could contain code that is buggy or malicious. In the slide, I'm showing the high-level picture of the NAB architecture. Components with a white background are new components that we developed for NAB, while components with a gray background are existing services that NAB uses as part of its architecture. The first component I would like to describe is the crawler, which essentially crawls and mines code repositories and also determines which projects are to be analyzed later. So it basically determines which projects match the user-defined criteria that I've talked about before. Then the dual component of the crawler is the analyzer, which is responsible for cloning code from repositories, building the code, and also running DPA on executable workloads. And assuming that the DPA can succeed, so assuming that the project can build, test successfully, and the DPA also can terminate, it saves results on a MongoDB database. Also, and not only results, but also metrics and execution statistics that are related to the DPA. In case of failures, the analyzer reports the reasons of such failures. For example, the code is, despite being managed by, for example, Maven, cannot build, or tests fail, or there are missing dependencies, libraries, wrong configurations, and many other things that can go wrong. And moreover, to present buggy, malicious, or non-terminating applications, the analyzer can be also configured with a timeout, which by default is of 1 hour, which basically terminates whatever code is running after the timeout is triggered. And this allows us to essentially continuing the analysis activities on other projects, even in case of problems with the analyzed code. NAB does not need any ad hoc dynamic analysis. Already existing DPAs can be executed on software projects with NABs, and this is made possible thanks to plugins, which essentially provide an interface for integrating existing DPA tools with NAB. Plugins essentially are composed of free scripts, which essentially serve to set up the environment, provide the commands to run the DPA tool, and if needed, also post-processing the DPA results. The master is the central component in NAB that orchestrates the distribution of crawling and DPA activities along the many instances of crawlers and analyzers, respectively, that can be deployed on the cluster. In particular, NAB assigns basically a subset of projects to be crawled from GitHub or from the chosen code repositories to the different crawlers instances. And then it also assigns projects matching the criteria to a given instance of analyzers to ensure load balancing. Another important component is a dashboard, which handles the deployment of NAB services using Docker Swarm. In particular, this is the component that initializes all the services container. It also allows to deploy on demand more or less instances of crawlers and analyzers, and also makes possible to for users to monitor the progress of a DPA. And finally, I would like to briefly describe the communication protocol in NAB. NAB relies on a published subscribed communication layer, which is based on a protocol called MQTT. And the MQTT broker that you see here in the slide is the core communication service that receives subscriptions requests to different topics from NAB components and redistributes messages that are published on such topics. And essentially, this ensures that the different components of NAB can communicate without knowing each other beforehand. So they only need to agree on specific topics. With NAB, we conducted 3 large-scale case studies applying dynamic analysis on public code repositories. In the first use case, we analyzed the use of promises in Node.js applications. In the second use case, we explored the presence of so-called JIT-friendly code patterns that I will explain later, still in Node.js applications. And in the third one, we use NAB to discover Java or Scala task parallel workload that are suitable to be included in a domain-specific benchmark suite. I will briefly describe each of the use cases, but I won't provide any in-depth details due to lack of time. Anyways, the purpose of the discussion is mainly to show that NAB can enable different kinds of large-scale analysis, and also that existing dynamic analysis tool can be integrated in NAB without the need of developing new ad hoc dynamic analysis. We conducted these use cases on 5 years of GitHub of projects hosted on GitHub. In particular, we choose Node.js, Java, and Scala projects whose last commit was between 2013 and 2017. And the total amount of projects matching this criteria is around 7.6 million. Then, on these projects, we applied basically given DPA tools according to the use case. And in total, the number of projects that we were able to successfully analyze with the DPAs is around 56K. The goal of the first use case is providing a better understanding on the popularity and the usage trend of the JavaScript Promises API, which is a novel language feature that enables better handling of asynchronous interactions in JavaScript applications. For this use case, we developed a new DPA, which is called Deep Promise. Essentially, Deep Promise analyzes a Node.js program and returns a set of promise chains for the applications. A promise chain is essentially an acyclic data structure showing the dependencies between promises and the values that resolve or reject each promise. In this use case, we focus in particular on the size of the promise chains, which essentially express the number of promises inside the chains, which can give us insight about the use of the promise construct. And we define as trivial a promise chain of size 1. And the reason is that such chains have no subsequent reactions to be executed asynchronously, which means that these chains are essentially not used to handle asynchronous executions. With Deep Promise, we were able to successfully analyze more or less around 23K projects. And the 25% of them use the Promise API, but only 10% of them use non-trivial promises, which indicates that most promises are not used to handle asynchronous executions. And we also determined that only the 0.6% of the projects use promises in application code, indicating that many projects don't use promise directly, but rather they rely on the promise support introduced by the other modules that they depend on. Regarding NPM modules, a total of 440 different dependent modules use promises, and we determined that around 400 of them execute non-trivial promise chains. The figure shows the most frequently used NPM modules on the x-axis that makes use of promises, and the modules that use non-trivial promises, which are those whose bar is on a white background, can be good candidates for further evaluation and optimizations. In fact, since these modules are used by many projects, identifying and optimizing a popular promise usage pattern in one of these modules can also lead to performance improvements in many existing applications. In the second use case, we aim at identifying bad coding practices that affect the application of Node.js performance. And in particular, we focus on the so-called JIT-friendly code patterns, which may prevent typical compiler optimizations. For conducting this use case, we used an existing DPA, which is called JIT-prof. And essentially, JIT-prof is able to detect 7 different JIT-friendly code patterns, and we use JIT-prof to detect them in both the application code and also in the dependent modules. The 7 code patterns that JIT-prof can find are shown in the table. We were able to successfully analyze almost 27K projects, and we found that the 30% of them execute at least one JIT-friendly code pattern. The most common pattern found is called inconsistent object layout, which indicates object access patterns that can lead to inline cache misses. And this is a sign, essentially, that more than 35% of the analyzed projects can perform read or write accesses to objects that can prevent compiler optimizations. And for this reason, they can cause performance penalty. Regarding NPM modules, we found that 900 dependent modules execute at least one JIT-friendly code pattern. In fact, you can see, again, here a summary of the JIT-friendly patterns that we are able to find. And unfortunately, many projects execute at least one of them. In the table, you can also see the number of modules where we found the pattern, and also the most popular free NPM modules where we were able to identify one of these patterns. The most affected modules are those three. They are called Commander, Glob, and Lodash, that you also find multiple times in the table because they are affected by multiple patterns. And we determined that these modules are imported by more than 130K other modules, which means that these code patterns can also be executed indirectly, not only in many other modules, but also in many other dependent applications. So to summarize the results from this use case, we have shown that Node.js developers, unfortunately, frequently use code patterns that could prevent or jeopardize dynamic optimizations, and so they can have a negative impact on the application performance. And finally, the purpose of the last use case is to show that NAB can locate workloads suitable for domain-specific benchmarking, where benchmarks from more established suites are not appropriate for specific evaluation needs. And the scenario that we consider in this use case is the one of a researcher who wants to analyze concurrency-related aspects. And for this reason, he requires task parallel applications for the JVM. In particular, here we target Java and Scala workload, which exhibit diverse task granularities, where granularity is defined as the number of bytecode instructions that are executed by a spawn task. For this use case, we resort to, again, an existing DPA, which is called TGP. TGP essentially is a task granularity profiler, which collects the granularity of all the spawn tasks. And in particular, it treats as tasks all the subtypes of runnable, callable, and fork-join tasks, which are classes or interfaces available in the Java class library. Regarding Java workloads, we were able to successfully analyze around 1.7K projects that contains task parallel workloads. The table of the right summarizes the different granularity ranges that we found in all these projects. And the main result of this analysis is that we found two workloads that spawn tasks whose granularity can cover all these granularity ranges, which is a sign of a high diversity. And for this reason, they can be good candidate workloads for task benchmarking. We repeated the same analysis also for Scala workloads. This time, we were able to analyze 860 projects containing task parallel workloads, and we found 3 of them spawning again tasks covering all the granularity ranges, which again indicate that these workloads can be good candidates for task benchmarking. So to summarize, this use case shows that NAB can help discover good candidate workloads satisfying domain-specific benchmarking needs. So to conclude, in this talk, I've presented NAB, which is a novel distributed infrastructure for executing massive custom DPA on open source code repositories. And we use NAB for conducting 3 different large-scale analyses on open source projects. Thanks to NAB, we were able to analyze the usage of promises in Node.js applications. We determined that many projects don't use promise directly, and we also determined popular modules that can be worth optimizing. We analyzed the presence of JIT-friendly code patterns in Node.js applications, and we found that unfortunately, developers frequently use them in their applications. And finally, we use NAB to discover task parallel workloads for Java and Scala. And in this use case, we were able to identify 5 candidate workloads to benchmarking task parallelism on the JVM. NAB is currently available as an evaluation version at the link that you see in the slide. You can also scan the QR code on your right. And feel free to contact me in case you would like to use NAB for your own evaluation need or just would like additional information about NAB or how to use NAB in your own, for your own activities. That's all for my talk. So thank you for your attention, and I will be glad to take questions.
Okay, so do we have questions?
So in the case study of the task parallelism in Java and Scala, it also looks like the range was sort of characteristically different, like it forms a different shape.
Yeah.
I wonder if you have any thoughts about where that comes from. It's just the nature of the 2 languages, the kinds of projects, or just this is the data we have.
Well, I also to say that basically such trends is, I mean, we found such trends quite, I think this trend is quite common. So in this case, so in this use case, we use bytecode as metrics for characterizing task granularity. And I don't know exactly why the ranges are like that, but I see that in general, most tasks somehow are either short or execute a moderate work, let's say. Tasks executing long-running workload are rather rare. And actually, I guess it's good that are quite rare because this indicates somehow, or this might indicate a lack of parallelism actually in the code. So yeah, we observe this trend. It looks like quite common. And yeah, that's basically what we observed.
Other questions?
So you said trivial promises are the ones that have just one application. Do you have any further information on non-trivial promises? Did you do any further analysis? Like what kind of other 2 applications, like if then, or is there any interesting patterns?
So we're mainly concerned about the size of the promises because, so here, let's say, we didn't want to consider promises that are not really used to handle asynchronous execution. So we analyzed the length of the chains, essentially. There is also another result that I didn't show here for lack of space, but basically we analyzed also the average length and the maximum length of the chains for each project. We were mainly concerned to see whether there can be, let's say, whether projects use more than 1 promises in a chain or not. So that's basically what we determined. Another thing that we determined is that most of the projects using only a single promise in a chain do that for things like version verification. So not really something that somehow you can chain together and can can give somehow some asynchronous patterns to be executed. So only something very simple.
Thanks.
I think we would have time for one more question. No more questions? Okay, then let's thank the speaker again.